Hi, I'm Derek, and in this video we're going to have a look at some data structures that I've been using recently to implement one of Xdebug's new features. Let me show you what I meant with what this feature actually does. The feature that I'm currently working on for Xdebug is called native path mapping, where I need to map a certain set of lines to different lines in a different files. So for example, if we have the following file, let me just draw that how it looks like. So we have this file here. And it has many lines. And then these need to get mapped to a different file, often a generated file, for example, a compiled template file or anything like that. That is often quite a bit bigger. And then what happens is that I need to map sections from one side to sections on the other side. So a simple one, for example, would be that, for example, line 2 maps to line 3 to 6 on the other side. Or, for example, line 5 maps to line 8 on the other side. Now these path mappings, what I need to store is, first of all, from which file, let's call it A for now, to which other file, which I call B. And then the line numbers map from 2 to, what are we saying, 3 to 6, and 5 maps to 8. Now, on the left-hand side and the right-hand side, it can either be a single one, like I do for 5 and 8, or it can move from 1 to many, like I do from 2 to 3 to 6, or it can also be blocks, like I draw that as well. So these two lines here, 7 and 8, then map to, say, 11 and 12 here. Now to store that, I need to store the starting line and ending line from each of those and map that to the start line and ending side on the other side. And this information is built up while parsing a file. One way of doing that is while you're reading the file, you can create a data structure called a linked list. So let's see how that would look like for our data structure. So on the left side, we have the following groups, right? When we are reading this, it reads first from file A. From file A, it reads start line 2 to end line 2, and then it maps to B 3 to 6. So this is one of my records. So when I read this record, I can create a data structure that has this information. Now the A and the B are already separately done, so I'm not going to bother much with that, because that is the file-to-file mapping. So I'm really interested in only the 4 numbers here. Now when I create a record, the data structure that I need to store, that I need to have like a starting pointer somewhere. Let's call it head. And then when I read each line, I will allocate this block here. So I will give that an address. This is an arbitrary number that I've just chosen. Now when I then read, and then of course when I construct this, I need to point the head to this one. Now then when I read the next line, I will create a data structure for that again, which I'll allocate in memory, where I will have on the left hand side 5 and 5, and on the right hand side I had line 8 and 8. Now of course, in order to read, and of course this gets allocated as well. A new structure, which is 10, and of course what I need to now do is link this one to the next one, so when I start reading from head, I can skip to the next line. So I have to add a record here. It's called next. And with this, I can then point to this address here by calling it. And when it is nil, then there's nothing further following. So when I read the list, I can then easily see that where I need to stop. We have one more record, so let me add that as well, which is line 7 to 8 on this side, which maps to 11 and 12 on the other side. After I've read this file and allocated the structure, I then need to update the pointer here. And then we have that sorted. And then this one is null. Now, when I now need to find a mapping, what I can do is I first find which file I'm mapping from. And for each file, I will have a separate structure. How I'm getting there, that's not for this video. But if I want to, for example, map line 7, what I need to do is I need to go to head, which points to this specific address here. I read that, and if the 7 is larger than 2, or rather than the end, then I need to go to the next record, right? So I will continue reading to this one. The 7 that I'm trying to map also doesn't fit here, so I now need to go to the next one. So for every element, you then need to go one further. Now that is of course not very efficient if you can imagine this is 1,000 lines longer, and I need to find line 199. And starting from the start every time takes up a lot of time. The further in the file you get, the longer it takes. So what actually would be quite clever to do here is to also create a cursor. And every time I read an element here and I know it matches, for example, so I know it matches 7. This is a random other address, is irrelevant. So anytime I update this, and for example, the last one I've read is now 7 and 8 and found a match here, I will leave this cursor pointed here. And then the next time I need to do a new mapping, which is likely the next number in the link. So I'm already having the cursor standing at 8. So I can update this every time to the address that my cursor is at. Now, if I found out that the number isn't higher, but lower, then of course I need to start back to the start. And if I read to the end, like I'm doing now, for example, read 9, then there's nothing next. I know there's no such line either. Now, the way of going backwards is also implementable by adding one more pointer to the list, which is not called next, but previous. So let me add those pointers too. We call them pref here. So when I read this file, I start allocating. Of course, the top one, the previous, is always going to be nil, so I can leave that filled in as 0. But when I create this structure, after reading the second line, I know that the previous one is the one with this structure, so I will fill in that address. And for this one, which means it then points this way, and then the previous one here is this address, right? So I can fill that in as well. So now, if I see that I found a number that is less than 7, I can then skip on backwards. So this is quite efficient to do, but there's one issue here, which is if you need to read random locations. The cursor is kind of handy, but it is kind of weird to do. Now, and there is a second thing here, is that allocating each of those elements every time takes up quite a lot of time. And every time you have the structure, you also need to have the next and the previous allocated as well. And these being pointers, they're going to be 8 bytes each. In addition to the numbers here, which is, well, I'm storing them as 8-bit longs as well. So that makes, if you count it up, you end up having that at 6 times 8, which is 48. But when I don't need the pointers, it will only be 32. That saves quite a bit of space, of course. Now, how do I make a better algorithm here? Now, of course, what I can do is, instead of having these next and previous pointers, I just allocate one single block of memory, which is quite an interesting way of doing it. because the way how this structure specifically works, you don't have really random access, right? So if I have a big list of 1,000 elements, then if I say I want to have line 400 in it, then I'd still need to start all the way to start. Or if the cursor is close by, I can't do it from the cursor, but I don't know that for sure. So this structure is called a linked list, or rather a double linked list, because I also have the links that are going backwards. And often what you also have is, besides a head and a cursor, you also have a tail pointing to the last one, setting up the right address in there as well. Because the tail is really useful to add new elements to the list, because I don't have to start all the way to the start. I can use directly to the tail, create my new object, and then set the next and previous pointers much faster. So this is called a double linked list. Which I also use in Xdebug, but for other reasons. Now, what is a better way of doing this? Which is something with a data structure called a vector. So instead of allocating different elements, what I first do is I will create a big structure up front. So say, for example, I found out by doing some kind of analysis that my standard file that I'm trying to map, or the amount of elements in the map, is 32. So what I can do is instantly allocate a block of 32 elements, which is not going to fit on my slide here. Allocate this in one go. So after allocating this and then start reading the file, I can then fill my elements, right? So this starts at 2 and 2. Now I need to check which one it was. That goes to 3 to 6. Then I have 5 and 5. That goes to 8 and 8. And then 7 and 8 maps to 11 and 12. Now every time I fill this in, I don't have to allocate any memory. I also don't have to update pointers because they're already here. The only thing I still need to do is, of course, remember for each file where this data element is. So if I start this again at this address, then my vector, as we call this data structure, needs to have a starting pointer. So we call it head again. Now what I also need to remember in head is how many elements we've allocated, because if we want to add one more here, I think I have allocated space for 4, 5, 6, 7, 8, 9, 10. So we know that our size is 10. So we need to record that. And what we also need to record is how many elements we currently have, which is in this case 3. So when we want to write our next element, we can calculate exactly what the address of that is, right? So if each of these is again 32-bit long, then we know that this one starts 32 bytes later, which would be the address in hexadecimal 20. So I know this instantly already what these are without having to do any calculations. The only thing I need to know is which element I need to put in there. So that is kind of an efficient way of doing that. Now the moment it hits, the amount of elements hits the maximum size, I can come up with a clever algorithm to either add 10 more elements or maybe duplicate the amount of elements that are allocated. Again, these are algorithms that depend very much on the use case. Again, just like it's a double linked list, in this case, I can also add a tail if I want to really. Although I don't really need to do that because I can just calculate the starting address plus 3 times the size of the amount of elements, right? So I don't actually need to have that because I can calculate this when you do 3 times 16 plus 1000 hexadecimal, and then you get to the right address again. But what this also allows me to do is to do a much better random access searches. There's no pointers to traverse up and down, right? Now let me add a few more numbers here to make it a bit more obvious and how this works. So bear with me for a moment. Now to do random access searches, what I can do is, of course I now have more elements. I have both the size is 10 and of course the amount of elements is 10. So let me fill in the addresses too. Hopefully I've done my hexadecimal math correctly here. But yeah, I know exactly how many elements in here. So for example, if I now start with this and I want to find the line mapping from 7 to 8 again. Now, what I can do is, of course, I can start at the start, and if the starting number is higher, then I can read the next one. So I can do a sequential search to that, which works, but it isn't the most efficient, especially if it is random access. Because if I know that I want to map line 39, what I'll end up doing is I need to read each of those separate and separate, right? So that's not very efficient. But what you can do is you can do a binary search through this. A binary search for this, for example, say I want to have the number 36, right? So when I'm doing my search, with me knowing how many elements there are 10 elements and then halfway, so we want to find the number, say 35 in here. So what I can do is like, well, I know how many elements in there, and the way how you do that is like a binary search is you start with the middle, which in this case, because there's 10, there's no middle. It can either be element 5 or 6. In this case, let me pick 5. So we start with the number 5. And we want to search for 35. And we can see here that the numbers here are from 10 to 13. Or rather, if I didn't mess up my writing there, from 10 to 13. Now the number 35 I know is higher than 30. So what I can then do is I separate the others that I have, because I still have these 5 left, right? So I can update this number 5 to the middle of these, which is 6, 7, 8. 8, and then I match this number, my starting number, with this range, which is 35 to 35, and then I found this on the second go. So it only takes me 2 attempts instead of having to start from the start, where it would take me 1, 2, 3, 4, 5, 6, 7, 8. So that's a lot faster. It's not going to be 100% accurate here, but you can see that if you have, for example, 1024 elements, which is nicely 2 to the 10th, you get to find any element in 10 elements because the search speed of this algorithm is called log2. So in big O notation, that would be O log n. So hopefully this was useful. I showed you my initial approach on how I did this with a double linked list, which works, but is quite a naive implementation because to find a element, you need to basically start searching from the start, unless everything you need to find is sequential, and then you can use this cursor that I used. And then the alternative one with the vector, where I allocate more memory in one go, which is a fairly slow operation sometimes, and then be able to use a binary search to find the element in there. So those are the 2 alternatives that I have. Xdebug uses a bit of both depending on the situation, but so it goes. Hopefully you found this interesting, so thank you for watching, and I'll see you next time.